Okay, so yeah. Anyway, um, as we mentioned like 2 or 3 weeks ago, whenever it was, this week we're going to talk about higher kinded types in system F omega. That's just what it's called. Anyway, in the previous, not last week, but last time we talked about type theory stuff, we talked about featherweight Java, which I'm not really going to recap very much because it's not very important for this week. It's sort of unrelated. And then 2 times ago, we talked about system F. System F omega is built on top of system F, which is why it's called system F omega, or one of the reasons it's called system F omega. The omega comes from something else. Um, so featherweight Java, I'm just gonna skip that, doesn't matter. So system F is this very simple programming language slash type system where we've extended the simply typed lambda calculus with these the for all alpha tau thing, these universal quantifiers on types, um, and and also the type abstractions and type applications. So system F omega takes that and adds a few more things. Notably, it adds these kinds, which are like types for types, basically. So you have the kind of types, and then you have essentially functions that take in types and produce types. And then we add a few other things, but I'll talk about those in a second. So the point of adding kinds is that then in the language we can define like type constructors. So like list is a type constructor, and having kinds lets us actually define like the list type in the language itself. Before we had like an abbreviation that we just sort of hand waved and said, when I say list alpha, I mean this, but now we can actually define it in the language, which is nice. Um, so yeah, so the extensions to system F that make it system F omega are just the orange things, but which maybe it doesn't look like too much, but actually it makes the language much more powerful. And I'll do some examples of that. First, I'll just talk through the syntax at a lower level. So kinds are either type or essentially a function from one kind to another kind. So for example, you could have like type, type to type. So this takes in a type and then returns a type. Or you could have, type to type to type. So this takes in a like type constructor that takes in a type and gives you a type. And you can do, however many nestings of whatever kind you want. And then the other new things are first, the for all alpha now has a colon kind. This is saying K is the kind of alpha. And we also added a similar thing to the expression level type abstraction. The big lambda alpha has kind K and then expression E. And then this is using the same lambda as the other one, which is maybe a little confusing, but this is how people typically do it. This is the type level function. So this takes in some type alpha with some kind K and returns a type. And then this is type application, just like we have application at the expression level here. That's a syntax. I also want to comment that a lot of times people will write like a star instead of type. I think that's more confusing, but it's nice because it's shorter and it's much nicer on like a blackboard, but I can just make a macro. So anyway, yeah, I'll talk about, we'll see examples of these things, but any questions before I move on?
Yeah, I mean, I guess I was just, I think it'd be helpful to see like a example of a type constructor because I don't like recall very well.
Yes, well, you're in luck. So here's this is like one of the simpler types you could make, optional. So an optional is like a value that may or may not exist. It's kind of like, value or null. Um, so in some sense, all the types in Java are like optionals. So essentially, if I have like an optional bool, that will be either none or some like true or some false. So the type constructor itself is this part, and then these none and some are called the value constructors. They're how you actually create values of type optional alpha or optional whatever. So let me just, so optional takes a type alpha, and then it produces and returns this type here. So just like with regular functions, when you substitute in a value for some variable, you get like the body of the function is the return value. Here, when you have a type function, when you substitute a type in for the type variable alpha, you get a type as the return value, so to speak. So optional bool is really equal to for all beta bool. I'll explain the encoding in a second, but for all bool, for all beta, given a function from bool to beta, and a beta, it will return a beta. So the idea here is basically that if your optional is sum, so it does have like true or false in it, then you apply this function, this function to get the beta that you return. And if it's none, so there's no value in it, then you just return some default value, which is this second beta. This is sort of the encoding of it, but yeah.
Wait, so what exactly is like beta in this case? Like,
Beta,
I feel like,
yeah, so the definition of optional, or the way you use optional, is that there might be a value, in which case you can use the value to compute, or there might not be a value, in which case you have to provide a default value. So beta is like the return type that, the return type that you want, basically. So if so let's say you want to do, you have an optional bool and you want to, I don't know, check if it's like true or not. So you have, first you have some true, and you want to check if the thing inside the type constructor is true, or inside the optional is true. So what you need to do is you need to essentially handle the case that it's some or handle the case that it's none. But in both cases, you're returning a Boolean, like, is this thing true? And that's what beta is. Beta is the thing you're returning, or the type of the thing you're returning. Sorry. So we have some other examples of functions that we'll implement, but essentially what you would do here is you would just you would pass in this function as the identity function, because this function gets run, that means that it's some, and then as the default value, you pass false, because if the function doesn't get run, that means it's none, so it's not some true. I will try and like run out some of these examples because it is probably a little confusing. But yeah, feel free to stop me, but I will, maybe it'll make more sense after we talk through the example a little bit more.
all right, sounds good.
So anyway, so first let's look at these. First let's look at none. So none is one of the constructors, value constructors for the optional type, which means that it's a function that gives you an optional. In this case, for any alpha, it gives you an optional alpha. And it can do this because you don't need any value to produce like null, basically. None is basically null. You just like write none, and that's the optional. So when you use, so let's say if we were to do none, and we wanted to, so we want to apply some function to it, and this will, sorry. Okay, so let's say we were doing a thing from before. So if we have none, the type we put here is the like return type of the expression. So I'm going to do bool, and then pass in the function that I'm going to use if it does have a value. I know ahead of time it doesn't, but it usually wouldn't. So this is my, so if it's some, it'll call this function. This just be an identity function. And if it's none, it will use the default value that I give it. So false. So if we sort of follow what happens, first I pass bool into none. So that gets substituted for, or sorry, I need to pass in bool twice, because one of them is what the optional contains, the other one is what it's returning. So first I pass in bool for alpha, so then this becomes bool, and then I pass in bool for beta, so this one becomes bool, and this one becomes bool. And then I pass in this function, this identity function, so that goes into f. I don't actually use f. And then I pass in some default value into b, which then becomes the result. So this thing will evaluate to false. So maybe I should go to my empty slide for scratch work. Okay. So the normal way that you use an optional value, let me go to case. Let me say you write like case, let's say opt for optional of some t, oh, why did I do t? Some x. And then you do something with x. You call like f of x. Or if it's none, you return like default. So this is like the way to use an optional value. Does that make sense?
Yep.
Okay. So essentially what we're doing is we're mirroring this structure, but like only using functions, because that's all we have. So instead of saying case opt of some x, then do f of x, otherwise do default, what we say is opt f default. Actually, sorry, I forgot what order I defined it in. It doesn't really matter, but I want to be consistent. So it would be, oh, right. Okay. Yeah, opt f default. Yeah, okay, that's what I had. So this is the same as this in a much more compact form. So the idea is if it's some x, then you call f on it. Otherwise, you return the default value.
Okay, makes sense.
And then the beta is just like a type annotation thing that you have to have, and it's just the type of default, or the return type of f, whatever you prefer. Yeah. So all these type annotations you like could leave out in the language like Haskell or something, because it'll figure them out, at least in this case. But in general, you can't figure them out. It's undecidable, so you just include them, or you make your language weaker. But that's not super important. Anyway, so sum is the other one. So here we just return the default value without calling the function. Here we call the function without using the default value. So we could just not have b, or we could call b anything and just ignore it, because all we do is call the function on whatever value is inside the optional, which I called a here. So using this structure implementation, we can define other functions on optionals. So for example, we can have this function called map, which takes, so for all alpha and beta, a function from alpha to beta, takes an optional alpha and makes it an optional beta. Basically, it just applies whatever function you pass to the value inside the optional, if there is one. And if there isn't one, then it will return none. So the so implementation, you take alpha and beta as types. That's pretty standard. You take the function that maps from alphas to betas, and then you take x, which is an optional alpha, and then you use this sort of this maybe weird encoding, but you do case x of some y, I guess, and then you do f. Sorry, do some f of y. Otherwise, you do none goes to none, like that. This is what the body is saying, but in a more conventional language. Yeah. And the point basically that I want to make is that the notable thing is that we have these optional alphas in the types of the language themselves now. So this is actually a thing that you can define in the language, whereas before we just had these like abbreviations that I technically shouldn't use because you can't actually write that in the language, but I was cheating.
Okay.
Yeah. And then here we have a last or another example function, which you can try and define yourself. So the idea behind this function is it returns true if the optional value is none, and returns false if it's some x or some y or whatever. So
Okay.
do you have any?
Let's see. Okay, so we have the type taking an optional alpha, and then you want to return bool. So then
So I'll start by saying that, so as a part of this, you can just sort of follow the type. So it says for all alpha, that means we need to take in a type alpha using one of these capital lambda type abstractions.
okay, and we wouldn't need to do that. We wouldn't need to do that for beta, right? Because there's none.
Yeah, because there's no
Okay.
beta. Yeah. There's a beta hidden in here, I guess. But yeah, and then because this is a function, we need to have like a regular lambda to take in the, or I shouldn't call this f, take in the this argument, the x optional alpha. And then here we need to provide some Boolean expression.
Okay. Then we would say, do we need to make use of any kind of like church encoding here, or?
Yeah. So this whole thing is a church encoding of an optional.
Oh, okay.
Yeah. So this is a church encoding. I just didn't mention it.
I'm not super sure.
Okay, sure. I mean, that's fine. Yeah. So okay. So we want to end up with a Boolean right at the end. And I mean, we're going to use x because it would be weird if we didn't. So I'm going to put x here, and I'm going to say the return type is going to be bool. So now I need a function, like some function f, and then a default value, let's say def. Oh, maybe that's a bad name, but it's a function f to call if x is some Boolean, and the default value to return if it's not.
Okay, then f would be true and def would be false, right? Or the other way around?
Yeah, the other way around. Yeah. So, well, yeah. So I assume by f is true, you mean it's a function that returns.
Yeah, a function that returns false.
Yeah, false. Yeah. So this is, it doesn't matter what it's called, but I'll say it's y, and then returns false, and the other one is true. Yeah. So I have that. Cool.
Okay.
So.
Oh wait, just like to clarify, the like that gamma, like alpha, just is like defining alpha.
Sorry, you mean this?
Like,
part?
Yeah, that symbol.
Yeah. So well, yeah. So it's capital lambda, but
lambda. Yeah.
So it's taking in alpha like a type as a parameter. So just like this lambda x is taking in x as a parameter, this is taking in lambda as a parameter. So when I pass in some alpha for it, it'll substitute in all the other places that you see alpha.
Okay.
So like the way I use is none is I have to tell it I have to tell alpha, which is the kind of optional that I'm passing it. So I'm going to pass it like an optional int. I have to pass int first, and then I pass my optional int, whatever. I don't know, opt int, whatever it is.
Okay, makes sense.
So yeah, I'll move on. I have more examples later, but for the moment, we're going to dive into the actual rules of the system. The evaluation is not very complicated in that it's the same as before. So for functions, all you do is substitute in the argument for you substitute in the actual argument for the formal argument, but you substitute in e prime for x in the body, which is e. And then for the type applications, it's the same as before. You substitute tau for alpha in the body e. And so the evaluation is exactly the same basically as before. I guess it's technically a little different because you have this k, but we don't need to worry about this here. This is just for type checking. Just like the tau is just for type checking regular expressions. So I'll move on because I think these are the same, but of course feel free to stop me at any point. So one of the two big new things now is that because we can do computations in the types, we either need rules to evaluate in types or we need to do some like type equivalence thing so that we can apply the type functions. So this approach I think is easier to understand, at least for me. I think this is nicer, but it's not as good for actual implementations, but we're not doing that right now, so I will just do this. So we're going to define this triple equals relation, which I'm going to call type equivalence. And all it's saying is that, when are two types equal? And for most types, they're equal when, they're exactly the same. So like if you look at this rule for applications, if tau equals tau prime or is equivalent to tau prime and sigma is equivalent to sigma prime, then tau applied to sigma is equivalent to tau prime applied to sigma prime. So this is what most of the rules say, and those are not very interesting. The most important rule is the EQ app, or equivalent application, I guess. Oh, sorry, I have two EQ apps. That's annoying. This is like a beta reduction, so I'll put a beta there. But this rule is the most important because it lets us evaluate the type functions. So if I have some type function that takes alpha with kind k and returns a type tau, and I apply sigma to that, then I get tau with sigma substituted for all the alphas. So this rule is basically just like all the evaluation rules for expressions, except things here are types and kinds instead of expressions and types.
Okay, sounds good.
Okay. So the other rules are just, all the parts have to be equal and then the thing is equal. So the other new thing is kind checking. Nobody really calls it that, but they're like kinding rules, but that sounds kind of weird. So in addition to type checking, we also kind check. So we type check our types. And this is the sort of the same idea as type checking expressions, is that if the expression type checks, then it will run. And this is saying if the type kind checks, then it will, like all the applications, all the type applications are okay. So if I have a type abstraction that takes in a type and returns a type, then I don't pass it like a type constructor itself. Hopefully that makes sense. So the other thing that should note is that the type environments, so these gamma, this gamma, before it just contained pairs like X has type tau. We're also going to stick in things like alpha has kind type, but it's sort of the same idea. So this first rule, this k var, is basically the same as the var rule for regular expressions, not regular expressions, but normal expressions. So if in the type environment we know alpha has kind k, then we can deduce that alpha has kind k. Then we have this abstraction rule, which again is similar to the regular rule. So if lambda alpha has kind k, dot tau, so taking in alpha, returning tau. So if when we know that alpha has kind k, then tau has kind k prime, then this thing is a type function, type constructor that takes in a k and returns a k prime. And then for the last rule, the application rule, if tau is a type function from k to k prime, then and sigma is a type with kind k, then we can apply tau to sigma to get a value of type, or a type of type with kind k prime. Sorry. All right. Does that make sense?
Yep.
Okay. And then we have these rules, which essentially make sure that when we are working with expressions, we don't have any type constructors left over because we won't be able to work with them basically. So here, if tau is a type and if sigma is a type, then tau to sigma, the type of functions from tau to sigma, is also a type. And if given alpha being of kind k, we know that tau is a type, then for all alpha of kind k, tau is a type. These are just making sure that we don't, for example, try to write a function that like takes like optional to like list or something, because these things aren't types, so you couldn't possibly write a function that does this in this system. Okay. And these are all the kinding rules. So now we just need to talk about the type rules, which are mostly the same as before, with a couple small changes. So the regular abstraction rule for these lambda functions is exactly the same as before, except we have to check that tau is actually a type. Because again, we don't want to say like x is like optional, or x is a list, but not a list of what. And then for the type abstraction rule, it's exactly the same, except now we just need to stick in the alpha into the environment so that we can look it up if we need. And the type application rule is the same as before, except now that alpha could be of kind k and not just like a regular type, we have to make sure that the parameter we pass in, tau, also has kind k. So as long as those two kinds are the same, then it works out. Just trying a lot of these hook things. And then the last rule lets us use the type equivalence that we defined before. So if we can prove that E has type tau, and tau is equivalent to sigma, and sigma is a type, then we can prove that E has type sigma. So essentially, it doesn't matter which type I pick, as long as A, it's a valid type, so it has kind type, and it's equivalent to something that I can prove that it has. So this is how we use the type equivalence to evaluate things if we need to. Okay. And that's all the rules. So that's all you need to get the system F omega and to get all of its wonderful expressivity maybe. So now I have a couple more examples to hopefully make things clear, because I feel like the definition is sort of deceptively simple, or maybe not deceptively simple, but unclear in what it really lets you do. So here's a foldable type. Foldable means that you can like sum it basically, where sum can be things other than just adding. You can, for example, you could like multiply everything, or you could do what we do here, which is calculate the length. So instead of summing, you're sort of adding one for each thing in it, and all these things.
Okay. Yeah, I'm familiar with folds from Haskell.
Oh, okay. Well, there you go. Yeah. So this is basically the same thing as Haskell. This is the church encoding of it. This is basically fold R. And then so, oops. Oh, this is not quite right. Sorry. And then this so I mean, what this is doing basically is it's taking, because in Haskell we type classes. We don't type classes in this language, so instead we're implementing them ourselves basically by passing in the functions that you need to implement the type class, which is how Haskell actually does it, like under the hood, but it has a nicer mechanism for it. But anyway, so the length function takes, so for all foldables f, so these are type constructors from type to type, and for all alpha, the type that the foldable contains, given the implementation of foldable for f on type alpha, we will, and if the actual foldable value itself will return a natural number, which is the length of the foldable, or the size maybe of the foldable, if it's like a tree or something. So to do that, we take in f, we take in alpha, we take in fold r, which is the implementation of fold r for this particular type. We take in x's, which is the foldable itself, and then we essentially use the fold r. Sorry, may as well just not written this. Okay, fold r, and then takes in, it's going to return a natural number, so I'm going to pass it nat, or natural number type. The function I'm passing it is x has type alpha, y has type n, or nat, y plus 1. The default value is 0, and then the list or tree or whatever, the foldable is x's. Okay, so this is basically like a Haskell program with a little bit more ceremony. It's Haskell program I have below, which is the point I was trying to make. But this is another type constructor you can make using in system F omega. Does this make sense?
Kind of, but not entirely.
Poorly explained because it was so poorly written. Yeah, so does the foldable like definition make sense?
Not quite. So I probably need to take some more time to like understand what each of the arguments are.
Mm-hmm. Yeah, so F is the like type constructor that is foldable. So for example, lists, maybe tree, I don't know, other things, sets probably. All sets are a little weird. Lists, trees, maybe these things are foldables. So F would be list, tree, or set. And then alpha is the type in the foldable. So if you have like a list of ints, alpha would be int. Beta will be the return value again. So this is the church encoding idea, where beta is the return value. So for length, I want to get a natural number out. So I'll put in beta, or natural number for beta. And then this is the type here is the type of foldar itself, but specialized to alpha, beta, and F.
Okay. Yeah, I think I get it now.
And then for length, so for all F, so F is again this type constructor, list, set, whatever. Alpha is the type in the foldable, and then this first argument, foldable F alpha, is the like implementation of foldable for the type F, which is a little bit different, I guess, from how Haskell does it, because you don't have to manage these things yourself. But sorry, this alpha also doesn't need to be here, I think. Let's see, alpha doesn't need to be there. Yeah, it doesn't. Okay, sorry. Yeah, so this is the implementation of foldable for the type constructor F. Then we take an F alpha, which is the actual list, set, tree, maybe, optional, whatever. And then we return a natural number, which is the length of the list. Okay.
I guess like, so the second argument makes sense to me, like F alpha. Mm-hmm. Yeah, but so when you say like passing in the implementation of the thing, is that like, I guess it makes sense. Like it's like an implementation that would take in take in the F alpha and then like be returning the natural number, or?
Yeah, so okay, so are you familiar with type classes in Haskell? I guess you're probably
No. Yeah, I've only like studied like a bit.
okay. Well, so I guess it doesn't matter. I'm not going to explain in terms of type classes, but so if I wanted to like implement like an interface in Java, right? What I do is, I write a class and then I, write all the implementations. The other thing I could do is instead of like implementing the interface, I could just, to every function that wants to use the interface, I can just pass it like a bunch of functions, where each function that I pass it is one of the things from the interface.
Okay.
Which is much more awkward when you're like actually programming, but it's much easier to like formalize. So if I have an interface, I don't know, like a collection interface. So I have like an add function and like a contains function, let's say, maybe just those two. So I could implement those two functions like normal, or I could essentially, I could give you two functions and I say, this function is the add function and this function is the contains function. And then anybody else who wants to use these functions on containers, you have to give it these functions to them. You have to keep passing them through the whole program.
Okay.
So that's what this is doing. So instead of having foldr like ambiently available somewhere in like the environment or like defined in some other file, I have to give you foldr.
Okay.
Every time I call the function.
That makes sense to me. So foldr is like contained in this foldable F implementation.
Right.
Okay.
Yeah. In this case, because of the way foldable is, there's only the one function. But it could be like, a record or something, or a like pair of functions or something. Yeah.
Okay. Makes sense.
Yeah. So I pass in foldr, which is the foldable implementation for F. Pass in x's, which is the thing, and then I call the foldr that I was given with this function that just adds 1 to the second argument, ignores the first argument, because all we want to do is just count how many. We don't actually care what's in the thing. Default value is 0 because an empty thing has length 0, and we pass in x's.
Okay.
Hopefully that makes sense. And hopefully my other examples don't have the same mistakes. Okay. Container, sort of. So this container interface is, this one's a little bit more complicated. It's like the, that's actually basically what I was saying. So you have a function, you have 3 functions. One of them is singleton. So given an alpha, it will give you a container that contains just that alpha. So like a list with just one element or something, or a set with just one element. It has flatten. So if I have a list of lists, then I can flatten it to get a list. And then map. So given a function from alpha to beta, if I have like a list of alphas, then I can get a list of betas. These are the functions that this interface basically has. So this is the container type constructor. This one takes a, well, I guess like foldable, it takes a type constructor like that, and then it returns a type. Okay. So C is the container type constructor. So again, list may be optional. I don't keep saying maybe an optional, but maybe optional, tree, set, etc. And all 3 of the functions I mentioned above, they don't have names here, just like a triple of the functions, or a pair where the left thing is a pair, but that's more confusing, I think. And that's what a container is. Or implementation of the container interfaces. It's these 3 functions. So again, using this idea that, instead of like having interfaces, I just give you the functions that you would use from the interface.
Okay. Yeah, that makes sense to me now.
Yeah. So one function to implement. I mean, there's a million things you can implement with this interface, but one of them is sometimes called flat map. So it takes some container type, some other types, So it takes a container implementation, a container containing alphas, a function from alphas to containers containing betas, and gives you a container containing a beta. So again, I think it's easiest if you think about this in terms of lists. So it takes a list of alphas, a function from alphas to lists of betas, and gives you a list of betas. So what it really does is it goes through each element of your list, applies this function, you end up with like a list of lists, and then you flatten it out. So for example, if I have, let's say I have a list like 1, 2, 3, like that, my function takes x. Oh, I can erase. Function takes x and returns, let's say, x minus x, like that. So if I flat map this function over this list, I get 1, minus 1, 2, minus 2, 3, minus 3, like that. Okay. So the implementation is essentially what I said. I took, I guess, a little bit more liberty with the syntactic sugar here than I probably should have. But again, we use these type abstractions to take in C, alpha, and beta. We take in this implementation called impl of the container interface for the type C, or type constructor C, sorry. We take x's, which is the container containing alphas. We take f, which is this mapping function. And we use the flatten from the implementation on the mapped list. So we map the function f over every element in the list or the container, and then we flatten it again.
Okay.
Does that make sense?
Yeah, yeah.
Okay. Cool. So that's flatten map, which is one of the functions you implement. But there are many others that we will not do. The other thing to mention is that this is like a monad. In Haskell, you would call it a monad. These names are more like Scala names, I guess. They call these things flat map and flatten and whatnot. In Haskell, you call it a monad, which I think makes it much scarier, but you know, that's Haskell people. And they call the functions peer or return, which is an even worse name, join, fmap, and they call this thing bind, but it's written like this. So anyway. Okay, anyway, I just wanted to mention that this container interface is monads. You can do lots of things that are not strictly containers, but are still monads. Monads may be a better name for that purpose, but containers. I don't know, does this all make sense?
Wait, what is the bit about, like, monad is just like basically equivalent to the container thing that we just talked about?
Yeah, well, yeah, they are actually the same thing.
Okay.
They're just different names. And my point was just that like calling it a container is like a little bit of like short selling what it actually is capable of expressing. But it is essentially just a container interface if you want to think about it that way.
Okay, got it.
Anyway, that's all I wanted to talk about because I also wanted to talk about stuff for next semester, but I was hoping there would be other people so we could talk about with more than one person. Because I don't want to make you like decide the fate of next semester yourself. But anyway, we can still maybe briefly talk about it.
Okay.
I think I'm gonna stop the recording now though, because